Exercise 3. Poisson distribution. If we do not know the number of elements subject to a certain risk, but we instead possess information on the average number of events that happen per unit of time, we might be able to use a Poisson distribution to count the number of elements that could probabilistically occur. A Poisson distribution only requires one parameter then, the average or mean frequency of occurrence. Place your cursor on cell B11. We will insert a Poisson distribution here to model the number of trucks getting damaged or out of order per year. Click on the Define Distribution icon. The following palette window appears. Select the Poisson distribution placed on the Common tab. The following window appears. To count the frequency or number of trucks damaged per month, we will use a Poisson distribution. A Poisson distribution always returns only integer values, with a mean and variance equal to its only parameter lambda. It is usually used to describe, for example, the number of individual events that occur in an interval of time when the events are occurring at a constant rate, the number of customers arriving in a queue, the number of accidents on a road, or the number of imperfections per meter of an item being manufactured, the number of items in a batch of random size, the number of items needed from an inventory, the number of periods, months, days a device is out of service, or the number of claims in an insurance policy. In this case, we are using it to stochastically count the number of trucks getting damaged per year based on historic information of the previous 8 years. Observe on the left-hand side of this distribution window that a Poisson distribution only requires one parameter lambda, which stands for the mean and the variance of the process to be quantified. Click on the three-dot icon button on the parameters window and click on Specify Excel References and direct your cursor to cell B21 when the following small window appears. Then, click on the upper right-hand side icon of this small reference window to return to your distribution window, which should now look like this. Move your vertical left delimiter to any place between the 0 and 1, and the vertical right delimiter between the 3 and the 4. This distribution describes how eventual random numbers will be generated during a simulation. By observing the values on top of the two vertical lines or delimiters, you should be able to already consider probabilities. There only exists a 9.3% probability that there will be 0 contracts per month, given that lambda, the average number of damages per year, is 2.375. On the other hand, there exists a 21.6% probability that there will be 4 or more damages per year, given that lambda, the average number of contracts per month, is 2.375. You can drag both of these delimiters to different values along the x-axis. Observe how the probability values on the bar on top move along, changing its corresponding points and their cumulative probabilities. Click on the OK button in order to close your window and return to Excel. The function on cell B11 should now look like this. Equals risk Poisson, open parenthesis, B21, close parenthesis. Make sure that your dice icon on your at-risks ribbon has been turned on. The random/static standard F9 recalc button. Click F9 to recalculate several times your randomly generated Poissons, and observe how values on cell B11 now change every single time you recalculate. This is proof of the random number generator engine that at-risk possesses, that is generating random numbers when Excel recalculations occur. Also, consider that certain discrete distributions can be adequately represented by continuous ones. For example, if your event to analyze number of cars passing a highway per day is discrete in nature, the number could be so high that a continuous approximation may give you a more adequate representation. For example, Place your cursor on cell B11, which contains a Poisson distribution. Open this cell with the Define Distribution button. Temporarily increase by overriding its parameter lambda with a 20 instead of the reference cell it currently contains. With a 20 as mean, the Poisson chart will look like this. Now replace it with a 200 and the chart becomes the following one. You will see how the distribution densifies itself and becomes more and more symmetric each time. As a matter of fact, it is converging towards a normal distribution function. Change lambda to 2000 and the chart will look like this after we change the x-axis around the numbers of the distribution. Therefore, when working with large numbers, a normal continuous distribution could be a good replacement for a Poisson distribution which is discrete in nature. Exit this chart by canceling the addition and returning to the original spreadsheet.